I started recording the meeting, and let's talk about what we are doing today. Hi everyone. This is I think the third session of Doctor Who, Doctor You. Today we're going to be talking about how scientists model the spread of diseases, specifically COVID-19, which is pretty important nowadays, as you guys definitely know. And yeah, we're just going to be making our own little project to use equations to model the spread of COVID-19. So first things first, we have to talk about how scientists model things in the real world. And we're going to talk about what modeling things means, and we are going to cover a bunch of math. So let's talk about what is a mathematical model, because the name of this whole session is mathematically modeling COVID-19. Okay? So scientists, there's a lot of important things that scientists need to study, except usually they try to like do an experiment and test things out in the real world, but that doesn't really work for everything. Like if you want to predict, okay, how would a disease spread in Houston, Texas, or in Chicago, you can't just release a random disease into the wild and see how it spreads, you know? You have to predict it without actually releasing the disease. And you might also want to do this like if you have a wildlife sanctuary and you want to see maybe how many rabbits are there going to be next year. There's no way to really do an experiment and test that unless you want to, you know, actually release the rabbits, or you want to, do a lot of complicated experimentation. Sometimes it's easier to make some sort of model, and we'll talk about what that means. And you can try and predict how things can happen in real life. So you don't actually have to release the disease. You can say, there's this many people in this city, there's this many office buildings, maybe this is how it's going to spread. You can say maybe 100 people will be infected in a few days, something like that. So usually what these models are is they're just equations. They're just mathematical equations that scientists plug into a computer with a bunch of numbers, and they try to graph the data and analyze it and see what they can learn. So they might have some equations to determine, okay, so for rabbits, there's like 12 rabbits that are born every week in our sanctuary. So how can we use that information to try and predict how many rabbits there will be next year? Something like that. And this is often done in conjunction with a computer. So you all often have a computer to graph the data and help you, learn, learn some information from that. Whoa, guys. Okay, don't draw on the thing, okay? Don't draw on the screen. Let me start sharing again. Okay. So, how do these kind of mathematical models work? So, essentially everything you can think of, it probably changes with time. So that's something really important. Like if you think about a ball thrown in the air, that changes with time because its position at one point, like 0 seconds after you throw the ball into the air, it's right above your hand. 1 second after, it's a little higher. 2 seconds, it's falling back down, something like that. And this is just like throwing a ball, right? But except it can be applied to really important things as well. The something that is changing over time can be how many people have a disease. It can be how many cells are in a tumor. So like if you want to track the growth of cancer in a patient, if you know what I mean. And it can also be things like how far an asteroid is away from Earth. Okay, so you want to know how fast it's coming at you. How fast is electricity in your phone being depleted, something like that, you know? So everything you can think of changes with time. And scientists want to use a special kind of equation to model this stuff. And it's especially useful in what we're going to do today. So these equations are called rate equations, and they're also called differential equations. So that's a big word, okay? But except differential just means it's pretty much a difference over time. Like if you have a ball that's 1 meter in the air at 1 second and 2 meters in the air at 2 seconds, there's a difference in the distance it is in between particular time periods. Okay. And same principle, if there's 100 people with a disease in 1 year, 200 the next year, that's also a difference. Okay. And rate just refers to how fast something is changing. So it's the same thing, rate equation, differential equation. They just refer to how something is changing over time. So the special word that we're looking at here is rate of change. So rate of change, I mean, if you just break it down, it's how fast something is changing. Is it like increasing at a certain speed? Is it decreasing at a certain speed? So rate is just how something changes in a period of time. And this is a little far from what we're going to cover today, okay? It's just we're building it up from the basics, so stick with me. So let's start with like the speed of a car, for example. So usually on your speedometer, it reads miles per hour, right? So that's saying like if it's 60 miles per hour, that's saying the change in distance is 60 miles that you travel in 1 hour. So that's a rate, for example. That's saying you're traveling at 60 miles per hour. And if you also look at something like the growth of a population of people. So in China, let's say there's like a million people being born in a year. That's not realistic, but something like that, right? So that's a million people, which is a change in the population in 1 year, which is the time period. So anything that you think about which is a rate is always going to have some change of something, and it's going to be in a time period. And this is going to be especially important when we're talking about the rate at which people get infected with like the coronavirus, COVID-19. If it's going really fast, then scientists would want to know if like there are 200 people being infected a week, if there are 100, and they need to like establish policies to take care of that, right? So before getting into the fancy equations that tell you how, like the equations that scientists use to model this stuff, let's start with the regular linear equation. And this is one that many of you may have seen in school already. I don't know what classes you guys are in, but most of you should have seen something similar to this in your math class. So if you don't know already, or if you just want to recap, so on a graph like this, you have two things that you call axes. Mel says boring linear equations. Yeah, it's boring now, but we'll get to the cool stuff in a bit. So yeah, so this is just a graph. On the up and down, you have something called the y-axis. And the y-axis is just, well, it's up and down, it's a vertical. And on this side, you have the x-axis, which it goes left to right. It's horizontal. So if you count like any point on this little grid we have here is marked by a particular combination of an x and a y coordinate. And a coordinate is just a number. So if you want to look at the point 2 comma 2, okay, like the 2 separated by a comma and then 2, that's going to be 2 in the x and then 2 in the y. So it's going to be this point right here. So hopefully this is familiar to you. If it's not, then we can go over it in a bit. You guys can ask questions as we go. So a linear equation. So you can see in this word linear, you have the word line. Okay, so a linear equation is just anything that draws a line. So in this case, let's look at the equation y equals 2x. So equals means they're the same to each other. They're equal. So for the equation y equals 2x, that means that it describes a line where the y coordinate, the y number, is always going to be twice the x number. So anywhere on this line, let's just pick a point. Eeny, meeny, miny, mo. This one right here. So can anyone tell me what the y coordinate is for this point on the line?
4.
Yeah, exactly. So Ria, so she just came into the meeting. She's asking for an explanation. So this should hopefully be good. It's like a recap for all of you. So scientists usually use mathematical models. They use special equations to model things in the real world, so they can predict what's going to happen in the future. So this is for Ria, by the way. She was asking in the chat for a quick recap. So we're just talking about a little build up to the kind of equations that scientists use. And the equations that scientists actually use are called differential equations. Differential equations. And they describe how something is changing over time. But before we can get to that, we just want to start off with linear equations. So yeah, I think Ishan said 4, and that's right. And the x coordinate for this is 2. So we're describing this point right here. And since the y coordinate is twice the x coordinate, that means that it falls on this line. So any point on this whole graph, if you extend it to like all the way in the negatives, all the way in the positives, all points on this line are going to have the y coordinate equal to 2 times the x coordinate. So that's just a basic description of what a line is, a linear equation. It's described by an equation which says the relation between the y coordinates and the x coordinates on that line. And then we also want to talk about slope, which is really important. So if you've heard the word slope before, you've probably heard it not only in math class, but in like a mountain or a hill or something you're climbing. So if the slope is really steep, that means that it's hard to climb. It's really vertical. But if the slope isn't that steep, then it's going to be something like this. Like I'm making it with my pointer right now. It's a little like flatter line, okay? So slope is just a word that describes how steep a line is. So right here, you can see that this line has a constant slope because it's the steepness of it isn't changing. It's the same steepness all the way throughout, okay? And the way mathematicians talk about slope is something called rise over run. So this is for every change in x, how much of a change in y is there? So if you change x by 1 over here, then y is changing by 2. If you change x by 2, then y is changing by 4. So I mean, if you go from 0 to 2, y goes from 0 to 4. So that's the slope. So if you go from 0 to 1, y goes from 0 to 2. So the bigger the slope is, the steeper that the line is. And again, the equation for slope is just a change in y for every change in x. So if the change in x is 2 and the change in y is 4, then the slope is going to be 4 over 2, which is 2. So hopefully you guys are comfortable with that concept. If not, you can just let me know in the chat and we'll go over it again. But yeah, that's just what slope is. So now we're going to get into, okay, well, we're going to get into a little more, okay? So in calculus, which is the field of mathematics that talks about like slope and area and a bunch of stuff like that, we won't get too into that, but they usually represent change with a d. So since I said slope is the change in y over the change in x, they usually just call it dy by dx. And you can think of the d as standing for difference, okay? So in this case, can anyone tell me, okay, so this line isn't exactly the same as we saw before, okay? We can go back a slide. You can see that this is the line before, and this is the new line that I have on this slide. So can anyone tell me what the slope for this line is? Just unmute and say it. Can anyone do it? Huh, okay. So the slope for the, yeah, sorry, go ahead.
It also 2?
Yeah, exactly, good job. So the slope for this line is also 2. So if you notice, the equation for this line, it's going to be 2x plus 1. So you can just get that because let's look at the point 1, for example, where x is 1. The y for this is going to be, well, you can't see it, but the y is 3. Maybe I should have picked a better point. But it's okay. If the x is 1, then the y is 3. So that means that the y is equal to 2 times this number plus 1. So it's the same principle. And you can see that even though the line is different, the way the line looks, the slope is still the same. It's the same steepness. So even though this, so even though this line and this line are a little different, they still have the same slope. And that's because the 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 principle of slope is for a linear equation, you have y is equal to 2x plus something. So this something, it can be 0, which is the case we saw before, where there's nothing added to it. It's just staying on this flat, on the 0, pretty much. And it can also be 1, where it's shifted up by 1. And it can be 3, or it can be any number, and the slope would still be the same. So I'm going a bit fast right now, but even if you don't completely grasp this part, it's a little fine. You know, we can go over it again. So this so far, this stuff is mostly basic, okay, and it's uh, it's really going to come in handy when you look at a more complex example. So in the real world, it's not just like, oh, we have 2 rabbits for every fox and it just keeps on growing, something like that. It's not really that way in the real world, right? So a good example of where differential equations come in handy is the change in y over the change in x is equal to y. So that's a little bit difficult to understand, okay? It's if you haven't seen it before, that means that the steepness of this graph is going to be equal to however high it is on the graph. So if you think about it, let's think of an example, okay? Let's say in a wildlife sanctuary or in a forest or something, you have a few rabbits, okay? The more rabbits you have, well, that's more, that's faster. That's a faster growth rate for the population. So if you have like 200 rabbits, then there's more rabbits to make children, right? So it's going to go faster and faster. But if you only have like 20 rabbits, they're not going to have that many children. So the growth of the population isn't going to be as fast. So that's an example in the real world of when the steepness of the graph, so that would be how fast the population is growing, is proportional to, well, it's sort of like equal to the number of how many of that thing you have in the first place. So hopefully you guys get that. I don't know if I explained that too well, but again, if you think of this y-axis as the number of rabbits, and you think of the x-axis as time, and let's say this is 1 week, 2 weeks, and etc. So it's 0 weeks. Let's say you have like, I don't know, 10 rabbits. And after 1 week, those rabbits have children and they have somewhere over here, like maybe 28 to 280 rabbits. And there's more rabbits there, right? So it's going to grow faster and faster. So you can see this line is going up and up, and it's going at an even steeper rate. So that's what I mean by the slope increasing. You can see as this y value is increasing, as you go from 1 to 2 to 3, this line is getting steeper and steeper. So this equation describes a lot of real world situations. So one especially good situation is the growth of a population. So this is where it's a really basic equation if you look at it. It's just saying the slope of this graph is equal to the value of that equation, you know? So this is called exponential growth. So maybe you've heard that word before. I'm not sure, but it's something really common in nature. So a good example, like I said, is just the growth of a population. Um, So now, yeah, before we move on, do we have any questions from you guys? You guys can go ahead and unmute because now we're going to get onto a little more complex stuff. So is there anyone who doesn't fully understand what like I'm talking about? Just go ahead and unmute and say it, or you can type it in the chat. Okay, Mel is good to go. A few others are good. Okay, so if at any point, it doesn't matter that we started this section, you can just go ahead and unmute and ask about anything, okay? So now we're going to talk about, well, we talked about the basic principle of mathematical models. So we did one model where it's like the growth of rabbits in a forest or in a sanctuary or something like that. So now we're going to talk about how scientists can model COVID-19. So this isn't just like, this is a really specific case of modeling. And we're going to have a bunch of different equations to model this, right? It's not just going to be like dy by dx is equal to y. It's going to be more complicated than that because you have people who are infected, you have people who aren't infected, you have people who have already been infected, so now they have immunity. So yeah. So the basic model that scientists use to model diseases, and in this case COVID-19, is something called the SIR model. So yeah, I mean it's like the word sir. Um, so SIR stands for three things. So there's three groups of people that this model splits the population into. It splits the population into a group called susceptible. So if you've ever heard that word before, that just means you're vulnerable. You're able to get the virus. You're at danger of getting the virus. So that's what susceptible means. It means you're able to get the virus. That means you haven't been infected yet. And the second group is the infectious or the infected. So that's people, as you can imagine, who have already been infected with the virus. And the third is recovered. So if you didn't know this already, you hopefully know it. But once you get a virus, usually, or not just a virus, but if you get like an infection for something particular, then you're way less likely to have that same infection in the future. So that means that if you've gotten COVID-19 and you've recovered and you're all good, then that means after you recover, you're not really going to spread the disease anymore. You're not going to get infected with the disease and you're not going to spread it. So in rare cases, you can still get the thing, you can lose your immunity, but that's not covered in this version of the model. So again, there's three groups of people. There's the susceptible people who are at danger of getting the virus, so they don't have any immunity or anything. So that's, if you haven't gotten COVID-19, then that's you and me and like most of the people here. So that's anyone who hasn't already gotten the virus. Then you have the infectious people who got infected with the virus and they're currently spreading the virus and they're moving around and everything. And then you have the recovered population, and these are the people who have already gotten the virus and they've healed. So a little tragic thing also is that recovered can also include people who, like, maybe really elderly people who died from the virus because they're just removed from the population that is able to get infected, whether they're alive and they're immune or if they're dead. So yeah, that's three groups of people, and you can see these arrows here. So what the arrows mean is you have susceptible people, and they're going to get infected at some rate. So that's going to be like if 100 healthy people get infected, like in the US, with COVID-19 every day, then that's like a rate of change, right, guys? So 100 susceptible people becoming infected in one day. Okay, so that's 100 people in one day. So that's exactly like the rate of change we talked about earlier. So there's going to be some rate at which susceptible people become infectious. So like just an average Joe walking around and he gets the virus and he's infectious. And then there's also going to be a separate rate represented by the second arrow at which infectious people recover from the disease. So if you have better medical care, then that means that this rate is going to be higher. You have like 200 infected people who recover, and this can be even worse. It can be like 200 infected people who die from the virus. That would also be under this same arrow. So this is just people who are infected who become a state where they are not able to spread the virus anymore. So they can either be recovered fully from the virus or they can be dead. So that's what this rate encapsulates. And you can ignore these for now. We're going to get to that on the next slide. But just remember, we have three groups: susceptible, infected, infected, recovered, and you have two rates of change.
What if, like, I don't know, I've just heard this somewhere, like the virus can mutate, possibly.
Yeah, yeah. So a
So
great
if you
question.
already if you already recovered from it,
Uh-huh.
would you still have a high chance of getting it if it mutated or something? Because the cells of the virus would change.
Yeah, yeah, dude, that's a really good question. So actually, this is beyond the scope of this video. Let me show you guys something. If I just look this up, there's actually going to be a little more of a complicated one right here. So this is the same thing we looked at before. So we have susceptible, infectious, and recovered, and we have two arrows. And then, like the person named Soup said, that's their Zoom username. You also have an extra arrow here, and this one is sort of special because it's like in a dotted line. And this is where recovered people can become susceptible again. So naturally, what happens is your body gets some sort of immunity to the virus because you have antibodies for that, and we're going to talk about that in a future session. Except what can also happen is one, the virus can mutate and it can become a new form where people aren't immune to it anymore. So that can be a case where recovered people are still able to get the virus. So they fall back into this group over here. And another case is that they just lose their immunity. So in some cases, like your immunity can decline because your memory cells just they aren't up to the task anymore. Your immunity doesn't really stay forever in some cases. Okay, so that's another case where this arrow exists. It's pushing recovered people back into the susceptible pile. So yeah, that's a really good question. We're not going to talk about that today, but great thought. We just want to keep the model simpler for now. Yeah, so again, we have this little diagram on the left to remind us. So you have susceptible people who can become infectious, and then infectious people can recover from the disease. And then you also have this invisible arrow that we're not going to talk about. So if you look here, you're going to see something a little more complicated looking, but it's very similar to what we showed earlier, where we had, for example, the dy by dx equals y. Except in this case, it isn't x and y. It's s, it's I, it's r, and t. So what does this mean? So the first thing I want to say is that this little t just stands for time. So if you wanted to say something like dv by dt, where v is velocity, then that means how fast the velocity of something is changing over time. So velocity means speed, pretty much, okay? So as an example, if I had the velocity of a Ferrari that's going down the highway or something, and dv by dt was 3, then that means the velocity is increasing by 3 meters per second every second. So that's just an example of something where it's d by dt. In this case, the d by dt it's the rate of change over time is going to be of s. So this is why we have three groups of people, okay? Because we have three different equations to model each of them. So ds by dt is just the change in s, the change in the susceptible population over some particular change in time. So an example of what ds by dt could be is and just to reiterate, if you're just joining the meeting, d stands for difference, okay? So ds by dt could be 100 people a year. So that means that you have an increase in this population. You have 100 more susceptible people like born every year. I don't know. It could also be negative, as you can see here. It's like we lose 200 susceptible people every year. So that means that 200 people are being infected every year. Because if they're going away from this population, that means they're going into this population and then this population, right? So if the rate of change of S with respect to time is negative 200 people a year, then that means that 200 people are getting infected a year. So does that make sense? Any questions? Oh wait, can you explain again? Okay. So again, we have three groups of people in the population, okay? Susceptible people who are able to get the virus. So that's just anyone basically who hasn't been infected yet. Then you have infectious people who have gotten infected. And then you have recovered people who have either gotten immunity from the virus or they died from the virus. So the first equation, so just ignore this stuff over here for now, okay? So these d things over here, ds by dt means the change in the susceptible population over time. So d again means change. So we have a change of 100 people, for example, over a change in time that's 1 year. So 1 year from now. So from 1 year from now, the number of susceptible people has decreased by 200. Then that means that ds by dt is negative 200 people per year. And ds by dt is just how fast the population of susceptible people is growing or decreasing. So does that make sense? Any questions? Don't worry about the right hand stuff for now, okay? So just any question about what ds by dt means, or di by dt, or dr by dt. So yeah, so S is susceptible, and then I is infected. And this is the change of infected people that you have per year. And then dr by dt is how many recovered people you have per year, like you gain or you lose. So can anyone like care to unmute and tell me what would make, let me see, what would increase the population of the I group? So what would make that population increase? The I group over here in the middle. So
Getting
what,
infected.
yeah, go ahead.
Suspectable going. Oh,
No, go ahead. I think you were on the right track there.
I'll let whoever was talking go.
Okay, sure.
I was just saying more people getting infected practically.
Yeah, exactly. So susceptible people getting infected. I think that's what Mel was about to say. So if the reason that the infectious population would increase, this I thing over here, the reason that would increase is because susceptible people are getting infected. So what this number just means, if you think about time as like 1 year, for example, what di by dt means is how many people are getting infected a year. That's probably the most straightforward one to understand here, the I. So if you have like the president saying, oh, we have only 100 people getting infected a year, then he's saying that di by dt is equal to 300 people a year. Okay? And the reason that we use the special d is it means it's just at that particular point in time. So let's say, okay, today, at this point, we're at a rate where we predict that 300 people are going to get infected by the end of the year. So this is just looking at a really particular point in time, a specific point in time. It's like if I went back, okay, it's like I have this curve over here, right? It's like if I chose a very particular line on that curve, and I would say, okay, this line is at a particular slope. So that's saying it's pretty much like at that very point what the rate of change is. So that's why I use this special D. So yeah, the infected population can change because more people are getting infected. And there's also one thing that we didn't consider. It's that the infected people recover. So when the infected people, they get healed from the virus and they recover, that's also that's also change in the population. So it's two things that can change the infectious population. Either people can join the infectious population by getting infected with the virus, or they can leave the infectious population by recovering from the virus and they can become, immune. So that's the first one we're going to see here. So it's like we have let's ignore this symbol for now, but we have a proportion of the population that's if you have a higher proportion of the population that's susceptible, and you have a higher proportion that's infectious, if you have a lot of people who are susceptible and a lot of people who are around spreading the disease, then that means that the rate of people getting infected is going to be very high. Actually, I got this little video for y'all. So this maybe should capture it in a little concise way. So let me just share computer sound. There you go. Can you guys hear that?
I can't.
Oh, okay, hold on.
Oh,
No, we can't.
Okay, there we go. It should be going now.
How can we model the spreading of a contagious disease?
Is that good?
yes.
Yeah,
Okay, cool.
that's fine.
A straightforward approach may be, how can we model the spreading of a contagious disease? A straightforward approach may be to model individual persons as either infectious or susceptible. If one infectious and one susceptible person meet, there is a certain chance that the susceptible person becomes infectious too. And then the first infectious person, as well as the newly infected person, further spread the disease. This seems to cry out loud for a spatial model in which we take care of the location of these persons. That would be complex. Luckily, there is another way. This is a much simpler way of thinking about such diseases, the SIR model. We do not look at the spatial distribution at all. We simply say that our population is made up of susceptible, infectious and recovered persons, and we only look at the total number of these persons. Susceptible persons can get infected and then become infectious. The rate of that process is controlled by the number of infectious people. The more infectious people there are, the larger the probability is that a susceptible person meets an infectious person. Hopefully people are going to recover from that disease, so there's a process that takes us from infectious to recovered. And in the standard version of that model, we assume that the recovered persons are immune and cannot be infected again. So they form a third compartment. This is a much simpler way of dealing with that problem. We forget about the spatial distribution altogether and simply construct a mechanical model, if you will, in which the population consists of three compartments: susceptible persons, infectious persons, recovered persons. Depending on the number of infectious persons, susceptible persons become infected and hence infectious, and after a while infectious persons recover. And we assume that recovered persons are immune against the disease and cannot be affected again. This is the SIR model, susceptible, infectious, recovered. How can we model?
Okay, yeah. So he said pretty much what I said earlier. Wait, can you guys hear me? I think you can, right?
I can. Yeah.
I can hear you.
Okay, there we go. So yeah, so he said pretty much what I just said, that there are three compartments in the population. There's like three piles of people, and the susceptible to infectious, there's a rate of change of people that become infected from the susceptible population. So that's like if you think about it, it's like when a susceptible person, like you or me, I guess, comes into contact with an infected person, like in the grocery store, there's a certain chance that the susceptible person is going to become infectious. So the higher that chance, or the higher the number of infected people out there, then that means that a higher rate of change of people becoming infected. So if you think about it, let's say like no one is wearing masks or anything, okay? Let's say no one wears masks and everyone touches each other all the time in public. So that means that there's a very high chance that when a susceptible person and an infected person come into contact, then that they're gonna infect the new person, like infect the susceptible person. And there's also a chance that if like a lot of infectious people are going out of the house and in a grocery store, there's like half the people who are infected, then there's also a higher chance that the susceptible person is going to become infected. So if you think about it, there's two factors controlling how how likely it is that a susceptible person becomes infected. There's the proportion of people. So a proportion is just a fraction, okay? So there's the percentage, I guess, let's say, of people in the population who are infectious. And there's also the likelihood that when an infected person and a susceptible person come into contact, that the person is going to get infected. So that has to do with, like, I guess, how frequently they touch each other, how, like, if people are wearing masks or anything like that. So there's two things that you should pay attention to here. Well, there's a bunch of things. The first thing is the letter N. So the letter N just represents the number of the total people in the population. So this can be like not just a city or something. It can be like in a store or in a school. If you have 1,000 people in the school, then N is 1,000. And then we also have this thing here. It looks like a B, and it's called beta, B-E-T-A. It's a Greek letter. So the beta is just a number. It can be like 0.1, 0.2, anything like that. And beta is sort of pretty much the chance that when a susceptible person and an infected person come into contact, that this person is going to get infected. So it's a probability. So if no one is wearing masks, then the probability could be like 0.5, like 50%. But if everyone is wearing masks, then it could be like 5%, like 0.05. So this beta number is going to be higher if there's a higher chance that a susceptible person becomes infectious. So if you look at this, we have I on the top and N on the bottom. So it's like we're multiplying S by two things. We're multiplying it by the chance of the person getting infected when they come into contact, and we're also multiplying it by the proportion, well, not percentage, but sort of like the fraction of people in the population who are infected. Because if either of those is high, then that means there's high likelihood that the person is going to get infected. So the way they model this is you take all these things into consideration, and you have this, you write these little equations, okay? So the rate of change of susceptible people is going to be decreasing by the rate at which people get infected. So if you have a bunch of susceptible people, as more people get infected, the susceptible pile is going to decrease. So this would be negative the rate of infection of people. So again, it's the chance, beta, multiplied by the number of susceptible people, multiplied by the fraction of infected people in the total population. So beta, the chance, times I over N, the fraction, times S. So that's how fast people are leaving the susceptible group. And if you think about infection, people getting infected, it's going to be pretty much the same thing. We have the chance of people getting infected as they come into contact. You have the proportion of infectious people, and you also have the number of susceptible people. And you also have people recovering and they're leaving the infectious group. So that's going to be a negative because it's decreasing the size of the infectious group. It's going to be a new thing. It's going to be a new thing called gamma. It's like this, and this has to do with how fast people recover, and that makes sense, right? Because if this number is bigger, gamma, then that means that people are leaving this infectious group at a higher rate, and they're going to this pile, the recovered group. So as people are recovering, then that also increases with this number, right? So as gamma, the rate of recovery, how fast somebody recovers, increases, then that means that the recovered pile is going to be increasing at a higher rate. So that's it for this little section here. So if you didn't get it, you can ask questions in a bit. So now we're gonna write some Python code, okay, guys? So to solve these differential equations, as you can imagine, these are really hard to solve by hand. So it's hard to just use pencil and paper and solve it like all by yourself. But computers can help us, okay? So usually computers, they split up the time into tiny fractions. So it's like if you calculate one number for each day in like a few months period, instead of calculating a continuous curve like we saw earlier, then it's really fast for a computer to do it. So like if you imagine this thing here, For a computer to calculate this curve, well, it might not be good in a number of cases. It might take the computer forever, and it might really be impossible for a human to do it. But in some cases, a computer can just pick a number for each little x value, like 1, and then uh, 1.2, and then go on, like a bunch of dots, and it can connect those dots later. So that's how we're going to write some Python code to solve these equations. We're going to use something called numerically solving. So numerically meaning they use numbers instead of trying to get equations and everything. So the computers just split up the time into like tiny fractions and then draw little dots on the graph, and they connect the dots at the end. So now let's try to write some Python code and simulate the COVID-19 outbreak using some numbers that scientists have gathered from the real world. So if I copy this link, I'll type it in the Zoom chat. So this is some code that I modified, that I sort of half wrote and half got from the internet. And this is based on some real life numbers. Okay, this is like a simulation. So if you guys click on that link, you'll see the example, and we're gonna try and code this ourselves. Okay? Yeah, go ahead. Someone was talking.
So if you're doing it on a computer, like if it's like I'm on an iPad right now, and if I press it, like I wouldn't really see the Zoom chat. So like if I'm doing it on a computer, like how am I supposed to go into the website that you're showing us?
Oh, wait, so you're doing it on an iPad or on a computer? Because if you do it on a computer.
So
Okay.
I'm doing the Zoom chat. I'm doing this Zoom chat on the iPad, and I'm doing the Google Colab in the computer.
Okay. So you don't really need to look at this document here. Okay, you don't need to click on the link. This is just as an example. So if you just follow along on your computer with what I'm doing on the screen, you should be good to go. Okay, so before we start this, any quick questions about like the model? Because that was pretty heavy. This is usually stuff that college students or high school students cover. So do you guys get the general idea of everything? Are there any questions? Okay, so it looks like nothing for now, but we'll yeah, any questions at any point you can go ahead. Okay, so you guys should go ahead and get Google Colab set up. Exit this link. So if you haven't already, just go ahead to Google Colab and sign in with your Google account. Saloni typed the link in the chat earlier. I'll just copy paste it again. Yeah, she pasted it too. So go ahead and click that and see if you can get set up with everything, you know? This just uses your Google account, so it's...
Are you talking to me?
No, I was talking to everyone.
Oh, okay.
Yeah. So I'll just give you guys a few seconds to get that stuff set up. And in the meantime...
So do we have to press it or just look at your screen?
Yeah, so you don't need to press the other link I sent you. The one Saloni just sent now, that's what you need to set up Google Colab if you haven't already set it up. And by setup, I mean you should just get to that screen where it asks you to create a new Google Colab notebook. If you're on that screen, then you're good for now.
So
Oh, was someone talking? Sorry. Okay. So hopefully you have it set up by now. If you don't, you can sort of catch up, and you can use the link in the chat that I sent you to refer to that, and you can copy that code as well and look at it in the future. For now, I'm going to go ahead and get started. So what I'll do is I'll split screen here so we can... Yeah. So this is where we're going to write our code for Python. So if you haven't already learned like a little bit of Python from Saloni's introduction, don't worry, it shouldn't be too hard. I'll explain each step as we're going, okay? So hopefully everyone is set up by now. I'll go ahead and get started. So just try to follow along and type what I'm typing. And if you have any errors, just unmute and let me know. Yeah, go ahead.
I'm not like set up for
It
the.
seems to work.
Okay, you're not set up for Google Colab yet?
Mm-hmm.
Did you sign in with your Google account and everything?
Not really. No.
Okay, I'll give you a few seconds. Do you know how to do it?
Not really.
Huh, okay. Let me see. So if anyone hasn't gotten it set up already, I will, hold on, I'll copy this. I should be able to show you how. So just click that link that Saloni sent you. Oh, sorry, yeah, you have the ability to do that. So just go to search up Google Colab on the internet, Google Colab,
Mm-hmm.
and you should be able to click the first link. So this is for anyone who's unable to like click the link because they're on a different device. So when you search up Google Colab and you click that, you should be able to sign in right here, and that should just get you started. So just sign in with your Google account, okay? Yeah, so the first thing we're gonna do, if you get behind, the code is on the right, and it's also in the link.
Wait.
Yeah?
I was talking to you. It doesn't say anything like sign up here. It only says share and.
You searched up Google Colab and you clicked the first link.
Yeah,
and,
I did, but like it's still not working.
Oh, right here. It should say sign in, right?
Yeah, but it doesn't say that. It only. Oh, I see now.
Okay,
I already
cool.
signed in, I think.
Okay, awesome. So the first step is that we have to import some stuff. So importing, it's just saying that we need some extra help, okay? I won't go too much into it, but if you know what it is, then we're just importing a few packages from Python. That we're gonna use NumPy, which is for math, and we're also gonna use something called SciPy, and we're gonna use a special thing for plotting called matplotlib. So let's go ahead and follow along here. So you're gonna type import NumPy as NP. So that means when you say the name NP, you're gonna be using the NumPy methods. But if you don't know what this means, don't worry about it for now. You can just type the stuff. It doesn't have to really do with the math of it. And then the next thing we're gonna type is from scipy.integrate. Oh, actually, you know what I'll do? I'll just copy paste this, because this isn't really important to the learning. It's just something you have to copy paste to get it to work. So I put it in the Zoom chat, so you can just type that, or you can copy paste it if you're able to. So so just again, I don't know if I said this, but just make a new notebook, okay? It should be like the first thing you see when you're on the page. Just click like make new notebook, name it whatever you want, and just type this code, okay? So when you're done typing, you want to press Shift Enter. So press the Shift key and the Enter key on your keyboard at the same time, and that should just run this little thing here. And it's split up into little boxes, so you can type different code in each box. And yeah. So this is where the
Wait,
import.
what did you do again? Because I was trying to catch up.
Yeah. Sorry. So did you make a new Python notebook in Colab?
Oh yeah. How do you get like the new box?
Oh, okay. So just type Shift Enter, Shift and Enter on your keyboard at the same time, and that should make a new box for you.
Oh, okay, thanks.
Yeah, no problem. So let's start off. If you remember what I said about the big N, so N is the total number of people in the population. Okay. So let's say in this case, it's an
How
output.
do you make your own Python notebook?
Let me see.
Because I couldn't really do it, and just.
Okay. Let me see. Okay. Sign in. Did you sign in with your Google account already?
Yeah.
Okay. So when you sign in, it takes you to a page like this, and you just click New Notebook at the bottom.
Oh, wait, just a second. 1 second.
Yeah. So anyone who's waiting, you can go ahead and see the code on the right if you want to if you want to type that up, and I can explain it in a second, or you can try to make sense of it on your own.
So we have to press new notebook?
Yeah, and then you can go ahead and start typing all this stuff. If you're trying to catch up, the code is on the right, okay? So you can just refer to that at any time. Are you good?
Yeah.
Okay, cool. So if you want to define like a word, or what in Python we call them variables, we're just gonna have to type the name of the thing and then type equals and whatever you want it to be. So in this case, we want big N, the number N we talked about earlier. I don't have it right now, but if you remember, the letter N just represented the total number of people in the population. So in this case, let's say it's an outbreak of the flu at a school, okay? So you have 1,000 people at the school. So that's gonna be our population in this case. And well, let's not say it's a flu virus. Actually, let's just say it's COVID-19. And then we have the initial number of infected people. So let's say one kid comes to school and there's only one infected person, and then that's where it all starts. And the way we're going to do that is we're going to say I0. So if you didn't know, putting a 0 after a letter just pretty much means it's the initial number. So at time 0. And that's not really like an official thing. It's just the way people usually do it. So you can say I0 equals 1. Because at time 0, so it's 0 days of after the infection, you only have one person who's actually there because he starts off everything, or he or she. And the recovered people, well, to have people who recover from the virus, you first have to have people who get the virus, right? So far, nobody has recovered yet. So our 0 is going to be set off at 0. So again, this means N, which is the total population, is going to be 1,000 because there's 1,000 people at the school. Then I0, which is the number of infected people that this starts off with, is going to be 1 because you have one person who has like COVID-19 and they come to school. And then R0 is the initial number of recovered people. So that's that third group, SIR, the R in that, okay? So you start off with 0 people because nobody has been infected yet. So let's just go ahead and leave that there. And then you also have the S, right? So you start off with how many susceptible people. So you start off with everyone in the population is susceptible, except for the people who have been infected. So if you're infected, then you're not susceptible anymore, right? So it's going to be the total population minus I0, and then also minus R0. So S0, the initial number of susceptible people, is going to be N, the total people, 1,000 people, minus the one person who's already infected, because they're not susceptible anymore, they're already infected. And then you have R0, which in this case it's 0, but yeah, if they're recovered, then they're not in the susceptible pile.
How do you add another box?
Press Shift and then Enter on your keyboard. So now we have the initial conditions. So we call these initial conditions, okay? So it's initially, before everything starts, how many of each group do we have? So now we want to talk about beta, which is that funny looking B that we saw earlier, and then gamma, which is that other symbol. So we want to set beta equal to the chance that an infected person and a susceptible person are going to come into contact and they're going to get sick, okay? So this is when a person with COVID-19, that one student who came to school, this is how much they're going to contact other people at that school and the chance that they'll get infected. So in this case, scientists have determined for this case that it's 0.2, okay? So this means that there's a 20% chance that this kid will come into contact with someone else and he'll get them infected. So that's what we call the contact rate. So beta, the contact rate, say that is equal to 0.2. And then one more little number, gamma, which if you remember here, I'll pull that up actually, hold on. So gamma is the recovery rate, right? So it's how fast somebody recovers. And the number here is 0.1. So actually what that means is it's 1 over the time that it takes someone to recover. So if it takes 10 days for someone to recover, which in this case it is, 1 over 10 is going to be the value of gamma over here. So this is the gamma, that funny looking Y thing. So we're going to say gamma is equal to 0.1 because 0.1 is 1 over 10 and it takes 10 days for someone to recover. Beta is 0.2, gamma is 0.1. And the final thing is we're going to do something where, if you remember earlier, I talked about how computers split time into tiny, tiny steps. So in this case, we have 160 days that we're going to model this COVID-19 infection. And we're going to split that up into like day by day. So the computer is just going to look at the number of population, like the number of people in each population each day instead of like infinitely small time periods, you know? So to do that, we have to tell the computer to split up time into into segments of one day. And the way we do that is with a special command. I'll actually copy paste this one. So we'll say this new variable t is equal to this funny command. It's called np, which is numpy dot linspace. And the way this works is you have a start number, and we start at day 0, and you have a stop number, we stop at day 160, which is the ending, and you have a number of segments, or like evenly spaced segments along that period. And this is how it's gonna know how frequently to split it up. So we start off at 0, so that's the first little thing, the parentheses, end at 160 days, and then we both have 160 samples in that time period, which basically means we just have one per day. So np dot linspace, and that stands for linear spacing, I think. So once you're done with that, just press Shift Enter, and it'll run that little box for you. And now we want to do, once you're done with that, now we want to get to the model. So this is the mathematical model that we talked about earlier, the SIR model. And to do that, we have to define a function. So if you, I think, let me look through the guests. If I'm right, a lot of you have went to the Python session, the basic Python session. So you should know a little about how this works, if I'm right. I'm not sure if you did functions, except, yeah, cool. So in this case, we're going to define a function that takes in the different the different values for the initial conditions, and it calculates what the rate of change is. So in this case, if you look here, you have the equations. So you have the S and you have the I and all that stuff. It's going to use those numbers that you plug in along with the beta and the gamma, and it's going to spit out these things, the rates of change. So it's like if beta is 0.2 and you have 1,000 people in the population and you have 200 susceptible people and 1 infected person, then this is the rate of change at which the susceptible people are going to decrease, like that. So to do that, to define a function, the first thing we do is we name the function. Def, and the name is model. And what do we want to take in to this function? What are the parameters, you might call it? So we want one parameter, y. And this is going to be a list. It's like a little array or a list. And this is just going to be S, I, and R. Y is going to be one variable that contains all 3 of these values. We also want a variable t. And t is gonna, oh, never mind. Okay, no, just kidding. Okay, t is gonna be the time. So it isn't used in the calculation, but it's still important for the rate of change. So we want one of these variables to represent the time. And this is gonna be, if you remember, t is gonna be the little grid, like the 1 day segments over 160 days. The other one we want is the n. If you remember, that's the total population. And we also want beta and gamma. So beta and gamma are just our, our little chance things, our rates, our probabilities that we put up there. So first thing is we want y to be unpacked into 3 different things here. We want s, I, and r to be the different elements of y. So this means that we're going to save the values of y, which is going to be a list of 3 different elements, into 3 things, s, I, and r. So you're unpacking it. That's what we call it. You're unpacking this list into 3 values. And now we want to type out these little equations. Because based on the values of s, I, and r, that's how we're going to calculate the rate of change for each of these, right? ds by dt is going to be negative beta times s times I over n. So we want to put that into equation form. So I'm going to just copy paste this for you in case you don't want to type it out, but make sure you understand it, okay? Guys, make sure all the spacing is lined up. I think I didn't paste it correctly, but the spacing should be lined up for this to work correctly. I'll paste it again. So just type that out. And if you can't type it out, sorry, if you can't copy paste it, just type it out. So again, while people are typing it out, I'll just recap. This thing, negative beta times s times I over n. So I over n is the proportion, the fraction of people in the population that are infected. Beta is the chance, the probability that 2 people will come into contact and one will infect the other. And S is just the number of susceptible people in the population. And in this case, you also have the same thing, which is how fast people are getting infected. And you also have something negative. So this is the rate at which people recover. So gamma is the recovery rate. And as that is increased, you have more people recovering, and the people who are infected are recovering quicker. So if you think about it, so I'm just waiting for everyone to type it out, whoever can't copy paste it. So I'm just rambling in the meantime. So yeah, if you think about it, all you need for this are you need a few probabilities, a few rates that we get from scientists who do their own, data collection. And we just need the initial populations. So you start off with, let's say, 1 infected person, and then you have 0 recovery. You start with 0 people who are recovered. You have a population of 1,000 or 1,000,000. And once you have that, you can do whatever you want. You can simulate everything. Okay, yeah. So Anna says she has a little error. It says S0 isn't defined. So make sure that you ran this box here. So make sure that you press Shift Enter after you type out all the code, because you have to run the thing for the variable to get defined in the first place. So make sure you do Shift Enter on this little box here, Anna, or you just press this play so you can run it.
It looks like it's 6:11 right now.
Oh, okay. Thanks for reminding me, guys. Adia. So, Selena, can you put the participation? Wait, Dhruti, what?
I said it's fine. We can go overtime.
Okay, yeah, thanks. So if it's Saloni, can you put the participation thing in the chat, please? So, since you attended this meeting, you can fill out the participation form, like the attendance sheet that Saloni is going to send in the chat in a second, and that'll just that'll just record that you attended this session. And if you want to stay overtime, yeah, for sure you can. And if you have to leave right now, but you still want to follow along with this code and look at what it does, I'll copy this again. So just try and save this somehow if you're leaving the meeting. And this is just the code that we're going to be using, that we're going to be typing. And you can play with the numbers and see how everything works out. You're going to see a graph like this. And yeah, you can just play with that. So Saloni just put the link to the participation form there. Yeah, so if you have to leave now, see you guys. If you're gonna stay overtime, glad to have you here. So just you can go ahead and leave if you have to. Okay, so for whoever is staying, Anna says she has a different error now.
You send the link to the leaderboard?
Yeah, we did. Saloni sent it in the chat. Oh, the link to the leaderboard? Hold on. I think Saloni's getting it. Hold on. Meanwhile, I'm looking at Anna's error. Oh, okay. So, Anna, I think if you're able to copy paste the code that I did, see if you can copy paste that, and then maybe you can save your code and we can look at the error after the meeting. Because in the meantime, I'm trying to get like everyone on the same page. But it would be an interesting error to look at after the meeting for sure. So now we have this stuff, and once we have all the equations made, like once they figure out the rates of change, we want to return these values. So this just means that this function is going to take in all these, and it's going to report the rates of change for each of these individual populations. So just type it and press Shift Enter. Yeah, Anna, you can email us with the link to your Colab thing, or you can take a screenshot or whatever. Let me type the email. Hopefully have it, but I'll type it anyways. Here you go. So once we define the model, which is just a function, we also want to, well, now that we have the model working, what we want to do is test it out with the initial conditions over here. So this is just the case for any general populations, but we want to test it for our case where we have 1,000 people. It starts off with 1 who's infected. So let's go and define the initial conditions. So y0, and y0 is just like a list, and y0 is going to be a combination of the s0, the i0, and the r0. So this is the state of our populations at the very initial time, like the very first point in time. So we start off with 999 susceptible people, 1 infected person, and 0 recovered people. And yeah, so y is just a random variable name. It doesn't really matter. We just use y as a representation of the state. Okay, bye. Hopefully you can follow along with the code at home. But yeah, glad to have you here. So now that we have this y thing set up, y is, if you're a little more advanced, it's a vector. So it's just like an array, okay, of different values. And now we want to solve it really quick, okay? So here's the command for this. I'll copy paste both of these so we can get it done quicker. So if you're able to, just copy paste this in there. So this means that this ODE int thing, that just means we're going to solve the differential equation, okay? So it's going to solve this equation, and it's going to use the model that we defined earlier, and it's going to start off with initial conditions y0. And y0 is pretty much a list of this thing, and this thing. So S, I, and R at time 0. It's going to use t, which is the time that we defined earlier, 160 days. And we have 3 arguments. We have n, which is, arguments are just pretty much constants that we pass into this. So we have n, we have beta, and we have gamma. So those are just numbers that we tell it. And then we save these curves. So this is going to have a bunch of dots, okay? It's going to be a bunch of dots in a big matrix, and we want to save these so we can graph it. So just type that out, or copy paste it if you can. So any questions about what anything means? Because this stuff is pretty advanced. Again, I'm just hoping you guys can handle it, you know, because I may not be teaching it the best either. Any questions, just unmute or type it in the chat. Okay. Oh yeah, how is y0 an array? Well, it's not actually an array. I just said that. It's a tuple. So when we say y0 is equal to this, this, and this, that's our definition. That's declaring the y0 variable. And that's why you don't use the little array brackets. It's you know, it's just a tuple, which is a special data type in Python. Okay, so what is the purpose of the ds, dt, and similar things? So if you're talking about in this model right here, yeah, so these are the equations from earlier, okay? So if you look at these things here, these equations, we just type that out into Python. So we made a function that says when we give it these numbers, it's going to spit out the ds by dt, di by dt, everything. Yeah, and then we are solving it with this command over here. So it's going to use this model with these initial conditions, and it's going to solve it over this time period. Okay, cool. So go ahead, press Shift Enter on that, or just press play. And hopefully it actually solved it in the background, okay? So it solved it and you don't even know it, so we didn't graph it yet. And oh, so Anna's asking why there's a capital T. So that's a good question. So when we solve it, this ODE-int thing, what it returns is actually a matrix. So it's a matrix of a bunch of different values that we're going to graph. And a matrix is just like a two-dimensional array, okay? So it's like for each time value, so we have 160 times, which is 160 days, remember? For each of those, we have a single point for each population. So it returns a matrix that represents each point in time, each population. And we want to do a dot T because we have to transpose the matrix. That just means we flip it around and make it easier for it to, we just make the dimensions line up right. It's a little bit difficult, but we want S to have all the values of S at each point in time. It's a little advanced, but T just stands for transpose, and you can look that up later. So if once you type this in or once you copy paste it, okay. Yeah, the recording is on our website. It's not on our website, but we're gonna put the recording on our YouTube channel, which we will put on our website. So once we did that, so what happened in the background just now is that it solved this whole equation. Now what we want to do is we just want to graph it, okay? So this is a lot of code, and it's not much that we can really learn from this besides just, you know, Python, I guess. So if you can, just try and copy paste this, okay? If you wanna do this for fun, then yeah, for sure. You can follow along, except I think it's gonna be too much time to type this out and explain everything, and it's not really much, you know, math or biology that we're learning from doing this. So I just typed it in the chat, so try and copy paste it. So what it's doing is it's just plotting all three of these. So right here we defined S, I, and R, and here it's just using the plot command to plot each of these on a graph. So S is plotted in blue, I is plotted in red, and R is plotted in green. So I'll copy paste it here and press Shift Enter, and let's let the magic happen. So right here you can see that we actually graphed everything. So isn't that cool? So right here is we can actually literally just plug anything we want over here. So let's say we want the population to be 1 million, okay? And we start off with 100 infected people. And we have the same things here, 160 days. If I want to, I can just play with the numbers however I want. And there we go. Now it changed. Now I have 1 million people. So 1 stands for 1 million. And then we have a different curve here. So, okay, hold on. Anna has an error. S is not defined. Okay, so the problem with that is this command isn't set up right. So S, I, R equals solved.t. So that has to be the problem. So yeah, so this is really useful for scientists when they model this stuff in the real world. So yeah, Anna, we will get to your error after the meeting. So actually just email us, okay? And I'll talk about it then. Because I think now we have to wrap up the meeting. We're a bit over time. But yeah, please email us and let's talk about that error. Because that sounds pretty interesting. I think that's a good opportunity to learn some Python. So yeah, so closing remarks. This stuff is really useful. So for example, like at the White House, when they're modeling disease and everything, they're using models like this. And so I think in the very initial stages of the COVID-19 pandemic, people are scrambling to get these statistics. So they're trying to get the beta and the gamma and how many people would probably start off as being infected and like that. So if you think about it, you have two different numbers here, right? The beta and the gamma that are really important that you can adjust. So the recovery rate, first thing, is something that you can adjust by having better medical care. So if you have a better drug, like you know, hydroxychloroquine, they were talking about that earlier. I'm not sure about the status of that, but if you have a good drug that can treat COVID-19, then gamma is going to be higher. So as people get infected, you're going to have more people recover faster. And if beta is decreased, then that means that you have a lower chance of getting infected or coming into contact with someone. So you can lower beta by not going out as much. So if you go to a grocery store very often, if less people go to a grocery store, there's a lower chance that they're going to come into contact with each other. So that's an example. Or they can wear masks and not touch each other. So that's a lower chance of getting infected. So that's why they say all those things. There's like two fronts, right? Two fronts of research. One front is they're trying to come up with ways to not spread the disease, which is beta. So social distancing, wearing masks, all that is under beta. So they're trying to reduce beta. And another thing is they're trying to increase gamma. So that means they're trying to find drugs and treatments that can increase the recovery rate of the disease. So using models like this can really tell scientists how the disease can spread and how they can eliminate it based on how they tweak these parameters. So in this case, you can see that you start off with a high number of susceptible people. And I just tweaked the numbers. I made it 1 million, but it doesn't really matter. You start off with a lot of people. And then as time passes, you have a wave of infected people. So this means that at 80 days, this many people got infected. At 100 days, this was how many people were infected. At 120 days, this is how many people were infected. Sort of like that. Lena says she copied this code, but it's not working. Okay, I think after these little closing remarks, I think I'm gonna have everyone who's having errors stay after the meeting, and then we can talk about those. So yeah, just really wrapping up. If you look at this graph, you can analyze it by yourself, tweak the numbers. You can see that over time, you have this little wave of infected people. And when they're saying to flatten the curve, this is what they mean. They're saying that this curve of infected people, they want to flatten this out. So you don't have too many people being infected in one day, because you don't have enough doctors to deal with like 100,000 infected patients in the nation, right? But you may have enough to deal with 10,000 one day, 10,000 the next, like that. So when they say flatten the curve, what they're saying is adjust beta and gamma so that this curve doesn't become too high and overwhelm the healthcare system. So that's where these kind of models come in handy. It allows us to use math to actually, visualize the way that diseases spread, and it's really important to scientists and I guess society as a whole. So this isn't exactly what they use to model COVID-19, but they did this in the earlier stages, and that's pretty much it for today. That's the lecture
How
part
do
of
you
the
run
thing
the
finished.
code?
Huh? What?
How do you run the code?
Okay, so yeah, once you type the thing, you have to press this little play button on the side, or you can press shift and enter. Okay, yeah, so while we're on that note, so the chat in the chat, we have the leaderboard link, we have the attendance sheet link and everything. So if you guys have to leave right now, yeah, go ahead. And here's the link to the code that I did, so you can copy paste that on your own time. Here is the attendance link. So if you have to leave now, go ahead and you can fill that stuff out. And I'm just gonna stay a little bit after for people who are having errors with their code, so they can screen share and work it out, because we have unlimited time now to figure that stuff out.
Do we have to do the code?
No, I mean, you don't have to do the code. You can. It's good enough that you stayed and you're listening to everything. And if you want to get your code working,
There's
you can
something
stay
wrong.
after. Yeah, okay. So whoever's having errors, stay after the meeting. And whoever's good with everything, if it's working for them, you can go ahead and leave now. So you can leave the meeting if you have to go. So right now we're just gonna look at everyone's errors one by one. So yeah, thanks for coming, guys. See you if you're leaving. And yeah, I'll stop recording.